Okay, good morning. So I'm going to talk about concurrency. And in a workshop like this, concurrency is a means to achieve high performance computing. So HPC is the main event here. And concurrency is one of many concepts required to get good performance. So that's one way to talk about it. The other way, which is what I'm going to use today, is to look at concurrency as the center, as the focus, HPC algorithms as one of the applications of concurrency, and there are many more applications also. Okay? So that's the viewpoint I'm going to take in this talk. And I'm going to talk about tools to teach such concurrency. And these tools can be used by the instructor, they can be used by students, and many of these tools can be used by both students and instructors. So I'm going to talk about these tools in the order I use them. Okay? And these tools include those that exist that others have developed, and then tools I developed to go and solve problems I saw. Okay? So this journey is sort of the tools I've used to teach concurrency over the years. And many of these tools are research tools. They are pretty complex, and I've published papers on them. And so this is going to be a little bit more superficial than the talks I've given for conferences in which I've published these papers. So the goal here is to connect these tools, showing how their designs and applications relate to each other. Okay? So not how they work, but what they can do. So let me first begin with just an IDE. Okay? So an IDE is, of course, great for any kind of programming, but I'm going to argue is particularly good to teach concurrency. Okay? And you see here why that's the case. What I've done is I've set a breakpoint in code that is executed by concurrent threads, and when the breakpoint is hit, in the stack frame, in the stack part of the programming environment, I see all the threads that are currently active. Okay? So I see actually a visualization of a thread. Okay? So for somebody who's learning how to what threads are, a concrete visualization drives home the abstract idea of a thread. Okay? So this is something when I've taught concurrency in PowerPoint slides, where I've told them, look, here's a thread, here's another thread, and explained what's going on. And in later, I've let them explore this visualization on their own. So I give them some code, and I tell them to set breakpoints and see what happens. So such an exercise I call a praxis. And to make the right things, I ask them questions afterwards to say, okay, how many threads were there? What were the threads? What were they doing? So that it drives home that there are actually, these threads that are computing to form the result, and so they see it very concretely. Okay? So what's great about this visualization is that it shows the internal state. It shows that this thread is actually a stack. Okay? Each thread has its own stack with a root method, and which is all hidden, of course, if you're using high-level abstraction. But if you set the breakpoint, you will see the stack no matter what, whether using declarative or procedural mechanisms. Okay? But what's not so good is that you don't see the threads in motion working. You see them stopped. Okay? So it'd be nice to also see the threads in action. And lots of you have taught sorting. And I hope some of you have seen the video Sorting Out Sorting by Ron Becker from University of Toronto. And the whole idea is to go and show the algorithm working dynamically. Okay? And you really understand what's going on. So inspired by that, I've extended this idea to concurrent programming. And you kind of see what I'm doing here, that these threads that I'm showing in this example are actually providing animations. And if these animations are visualized, then you see the threads acting dynamically also. And here's my first animation. And this is so what we're doing is we're simulating physical world, and the threads are, in this example, you can have, the real situation is two pilots flying different planes or shuttles, and so the simulation has two different threads controlling the two shuttles. And let me just play the video to show you what's going on. So So the fact that they're flying together is an indication that two threads are working together. Okay? And so here's one thread, here's the other thread, and that's what happened in the video. Things get more interesting when there's race conditions. Okay? And so in this case, you have also two threads, but they're both controlling the same shuttle. Okay? It's like a pilot and co-pilot not being aware of each other and flying the same plane. And you can imagine what will happen when you have two independent animations controlling simultaneously one shuttle, and you'll see the shuttle oscillate. Okay? And let's see whether that happens or not. So this is very concrete illustration of a race condition. Okay? And we can do the same thing now with synchronized threads. And the first thread does its job, locking the shuttle, and now the second thread does its job. Okay? So you see how a critical section can be implemented here. Okay? So this is like a pilot and co-pilot taking turns. Here's a variation of the first scenario in which we again have two threads controlling different shuttles. And I've added a third thread, which is a controller of these two threads. Okay? So these two threads will go and wait for a signal from this controlling thread before they go and start the animation. Okay? So this way they can understand wait and signal. So let's go and play the animation. So the first thread is waiting, the second thread is waiting, the controlling thread says go ahead, signals it. When it reaches a certain height, it signals the other thread, and so you see wait and signal very graphically here. Okay? So controlling threads, signaling waiting threads, a la like an air traffic controller controlling. And so, concurrency is not so hard if you think of the fact that we're all actors that act concurrently, and the fact that I'm similar in the real world makes that drives the point home. So if you know something about signaling, you know that there's a notion of broadcasting also. So that's what's going to happen here. That when the proceed button is pressed by the controlling thread, both shuttles will at the same time get dequeued from the. So this thread is waiting. I proceed all now, and they both start flying. Okay? So basically, all the threads in the queue get dequeued. So I talked of queues. Visualize queues also. So I built a tool that goes and visualizes the queues. So you see these two threads waiting right now, and here's a visualization of these two of the queue in which these two threads are into which these two threads are queued. So when I do proceed, one of the shuttles starts moving, and you see the queue has this other thread. When I do proceed one more time, the queue is empty, and in this case there are two threads in this queue. I do proceed all, and the queue gets empty. Okay, so again, these are pretty advanced concepts according to some people. Okay, but you show them this way, and you can teach them to freshmen, which is what I've done. Okay, and so this has worked pretty good for me. So how do you use this? Well, you can create videos of this and show it to the students, like the sorting video. But these are Java programs that can be actually manipulated by students and instructors, so they can actually run them themselves, manipulate them, and see what happens. Okay? And so you can actually change them, and you can make a method synchronized or not synchronized, and see interference or not interference. Okay? Here in this praxis, I tell them, okay, remove the synchronized keyword, go look at what happens, add it back, and answer some questions. So this way they get the point while coding. What would be even nicer is if the students and instructors can write code that builds these simulations. Not just take these canned simulations I have written, but to build their own simulations. Okay? That's what's happening here. I'm not sure how much of the Indian audience is into Monty Python, but I am into Monty Python a lot, and my American students are very much into it. So this is a scene from Monty Python and the Holy Grail. And it doesn't matter if you don't know about Monty Python. What's important here is that each avatar here is a separate thread. Okay? And there's this controlling avatar who's clapping, and with each clap, these other threads are supposed to march. Okay, so they coordinate with each other. So this is like the air traffic controller, except that it's controlling every beat. So that's what should happen here. So this is the last project in a series of assignments students do, and it's, they're pretty happy when they get this part working, and it's not easy to get this part working. So avatars move in lockstep. So, making students implement these assignments, they're fun. Okay? Especially if you like Monty Python in this project. But if you have to go and create all this visualization, it's going to be tedious to implement and not doable, actually. So what you do is, what I've done is, I've used what in software engineering is called the observer pattern, and what in common language is often called the publish-subscribe model, where you have an object that an object that creates events to which other objects can subscribe and be observers of. So the creator of events is an observable object, and it has methods to register the observers. And whenever the state of this object changes, a notification method is invoked in the observer, the subscriber. So if x becomes 10 in this particular object, then you get a notification that x is equal to 10. Okay? Now, the students write only the observable models. Okay? So they will create the shuttle image. They'll just get a shuttle image from somewhere, and they'll move in a loop, they will move the coordinates, which is not hard to do. And these events are broadcast to the observer, object editor, which is the tool I built. And that will go and display the objects and go and update the screen. So implementation is not that hard, as long as you can create an observable model. Okay? And I teach this stuff in an object-oriented programming course, so they get to know about the design pattern also and get this concurrency stuff working. Okay? So object editor automatically displays shapes and moves them in response to observed actions. Okay, so like I said, it's exciting to students. And another good thing is that whether concurrency is working as expected is apparent in the user interface. You don't have to look at the code to figure out whether you've done the right thing. Okay? If they're not moving in lockstep, or if they're not moving at all, then you know that they're either failing in coordination or they're failing in creating threads. So assessment becomes easier. So debugging and testing becomes easier. So the student is testing on their own. They can see what's going on in the user interface to figure out what the problems are. If they need help, they can come to an instructor who can go and see what's happening in the UI and then tell them probably what's going wrong. Okay? So programs actually become easier to, sorry, I have this thing it'll go off in a few seconds. So debugging and testing potentially becomes easier. And at some point, they have to be graded also and given a grade. So the final submissions also, the instructor doesn't have to go and look at the code to figure out whether they've got concurrency in there or not. They just look at the UI. Okay? But they have to go and navigate from one student to another student. They have to go and have a rubric and give them points. Okay, the threads are moving, but they're not moving in lockstep, so take off points for coordination. So that becomes a bit of a challenge. Okay? And this tool gives you automatic navigation rubric management support. So you can just press the next button to go to the next student, or previous button to go to the previous student. And you have a rubric which says, okay, these many points for this feature, this many points for this feature. Okay? And if you ever use something like GradeScope, that feature is provided by web-based systems also. Okay? So they came later than my tool, actually. But what's good about this tool is that it's not web-based, so I can press the run button, which you won't have in GradeScope and other tools. because this tool is running on the desktop computer, and you can run the program, see the UI, and once you're happy, then go to the next program, see the UI, and students go and actually create canned animation, canned movements to sort of illustrate what's happening. Okay? So you don't have to go and interact with the application. You can, but students are supposed to actually write a piece of code that demonstrates what the dynamics of the simulation. So that's good. We used this for a long time. And then, we said, can we do better? Can we avoid the manual inspection step also? Okay? And in theory, that should be happen, right? If my eyes can observe what's happening and figure out whether there's concurrency or not, surely an object can also do it. Okay? So, on the observable model situation concept, not only is the object editor observing the actions of write methods, but so are observer tests, so test code that I wrote, and they're also observing what's happening. So if some thread goes and invokes a write method here, the same thread will also invoke the notification method here, and the tester can say, can figure out which thread invoked some method, and keep track of what threads are active and what they're doing. Okay? So here's another thread, and so another thread is invoking the notification method. Okay? So my testing code then becomes multi-threaded, right? Because it's being called each time the tested code invokes the write method. And multi-threaded code is complex. So this testing code becomes complex. Okay, this is what I did initially, and then I said, let's build some infrastructure to handle that. So I won't tell you exactly how that works. But the whole idea is that my custom test is only single-threaded. I built a whole layer here that's multi-threaded that goes and keeps track of the events that are received, and then the custom test can go and query and say, well, is this thread sequence interleaved with another thread sequence? So it gives you very high levels, much higher level support to make this thing happen easier. Okay? And I have written a paper where I've shown that there's a big difference in the amount of code you write using these two approaches. Okay. So this is all concurrency centric. What I've shown you is how to do simulations. Where's the high performance computing here, right? So let's go to high performance computing. High performance computing is, as Sheikh was saying, this SIMD model, and it involves fork join abstraction often. So you have a dispatcher thread that's given some piece of work, and it goes in partitions that work among worker threads. These worker threads synchronize with each other to go and write data to some shared state. And then dispatcher thread, so I think I've got some animation here. Okay, no, I don't. So, and dispatcher thread then produces the results. Okay? So, the problem here is that whether you have one thread or you have multiple threads, the result should be the same, ideally. Okay? So if this is the input and this is the output, if it's correct, you don't know whether it was correct because there were multiple threads or there was single thread. Okay? So was there concurrency with the correct solution? And if it's wrong, you don't know whether the sequential part of the program, worker code is at fault, or the synchronization part of the program is wrong. Okay? So what's the reason for error? Sequential error or concurrency bug? Okay? So how do we solve this problem? That's why I was going to the simulations, because there you see multiple threads and they're supposed to do different things. Here, that solution is thread aware, and this the user interface is thread aware, and this user interface is not thread aware. So what do? Well, we cheat. We tell the worker threads to go and trace their actions. Okay? So every time it does a computation in a loop, it goes and says, okay, this was my input for in this example. This is a prime number example, I think. It says, yeah, 3 is a prime, 5 is a prime, and this thread says, oh, I got 18 and it's not a prime. Okay? And from this, you can tell, in this example at least, that the sequential code is fine, and the reason why 5 doesn't appear here is probably some synchronization issue. Okay? So, so with these traces, you can actually go and write test programs that test the fork join model programs also. Okay, so what did we do? I built on what I already had. So the program is just a sequential program, no objects, no observable, nothing. It just has print line. Okay, this is a Java program. It does system.out.println. and I cheat and I go and make system.out point to something I wrote. Okay, so they think they're printing out the Java system.out, and I'm printing it out to my system. My tool is getting it. And my printing object is an observable object. Okay, so whenever it gets a print, it goes and broadcasts that fact, and that can be given to the testing code, which can then go and figure out whether the traces were correct or not. Okay, and then I created some extra infrastructure specialized for the fork join model. Okay, so the previous infrastructure was meant for any multi-threaded program. The specialized, and what happens now is that the test code just figures out, writes down the what of the concurrency's requirements, just specifies that. And there's infrastructure that figures out how. It figures out, it collects the trace, it checks the syntax and semantics, that the right values got input and output so that you can parse them. It figures out the correct number of threads forked based on what this particular specification said was the number of threads. It makes sure that the threads were concurrently executed, it makes sure the load balancing, outputs error messages. Okay? So that kind of works. It kind of works because I've had limited number of programs for which I've written tests. Okay, now let me switch gears a little bit related to tests. So these tests can be run not only by the instructor to grade, but by the students also to get feedback. Okay, so they become like an extra instructor, and this is very. I mean, the students really want this, especially if you're not building visual programs, especially when you're building these textual programs that don't quite show concurrency. And what I do is, every time they run a test, I log the action. And this log data can be then visualized, which we haven't done quite, at least we don't do it in real time. And that data can be looked at by the instructor, who can do many things with it, including helping students who seem to be struggling. Okay? So we get test-based awareness, which is, so if you're like me, I give an assignment, and then I'm in panic. Are the students working on it? Because my assignments are hard, and they have to start it quickly, and I'm worrying, have they started? Are they having any problems? And with this logging, I can know what's happening. Okay? And so this is visualization of unseen work that would otherwise be unseen. And this is some visualization we have created after the fact. And I won't get into details of this, but well, let me just spend maybe a second here. So on the x-axis is what score they got on a concurrency topic, students got, like threads and position coordination. On the y-axis is how much time they spent on it, testing. And what you see here, except for some exceptions that are labeled, as you spend more time, you get higher score, which is good. It's good to know that it's work that's stopping them and not some other issue. And it also showed, we built these plots for all topics, that low effort hurts synchronization and coordination more. So they are more complex topics than just creating threads. Okay, it's like learning to drive is easy. Learning to be a good driver in traffic is hard. Okay, so so that Tesla will tell you that. So here's another visualization we created after the fact, and this is something in which Sheikh was involved also. So we ran a faculty training workshop at Tennessee, and here I'm visualizing what happened to each participant. So each participant is a row, and the participants had two goals, and whether they achieved the goal through tests or not was shown through colors. So there was the blue goal and the purple goal, and the size of the circle tells you how much testing they did, and this was very revealing. So most did not. They were given 90 minutes, and most did not complete both goals. And so I wanted to know what was going on. And you see the three people who finished, they had varying strategies. Okay, so this person has a very fat purple circle, so they did a lot of testing. This person has a very thin one, and the ones who did not, and there were people who worked quite a bit and didn't achieve the goal. So these are people who could have used some help. And there were some people who didn't finish because they hardly worked. Okay, so you see this, the x-axis is the time, by the way. And this person just ran the test once and did nothing else. So if they didn't finish the exercise, I'm not shedding any tears, right? So you can get, so in any kind of training or teaching, you want to get some data. And here's a rich source of data that people haven't looked at much or at all. in the literature. And we found there was a substantial difference in time spent, milestone achieved, testing strategy used, and so there was a lot of interest. Okay, so even though there was one person who spent a lot of time without achieving their goal, Sheikh had a bunch of TAs helping people with their work, and so here we had everything done through Zoom, and we sort of figured out how much help they needed. But this brings me to the AI part, that wouldn't it be nice if we could provide help not through Sheikh's TAs, but through AI? Okay? And so let's try to see whether that's a far-fetched goal right now, whether it's a goal towards which we should work or not. So the problem that they were given in that workshop in Tennessee that they didn't finish was to take a sequential prime number processor, there was code that they were given, and convert that into a parallel prime number processor. So I just asked ChatGPT, well, we used GPT 3.4, 5 and 4. Can you go and use the fork join model to convert this program into a concurrent program? Okay. Now, concurrent fork join prime number application probably exists in somewhere in the web. So the fact that it could do it is not such a big deal. But what is a really big deal is that it used all the code that could have been reused from the sequential part. And so the solution it gave was very specific to the task it was given and not some generic thing it spit it out. Okay? And I was blown away by everything AI did, by the way, that I tried to make it do. So this is emulating the human task. Then there's this other paper that I'm supposed to present at 12 o'clock, I guess. And that's a variation of this exercise where they're given a concurrent program and they're asked to go and fix bugs in 3 procedures. Okay? Actually, there should be odd number. I cut and paste, there should be odd numbers here. So both 3.5 and 4.0 corrected all of these 3 procedures, each of them, okay? And while reusing all the code that could be reused. So this is very specific to the task they were given. They didn't just spit out something that they were programmed. Okay? So this is a task that some of you have actually done, and you're supposed to answer quiz questions on the code. So I asked ChatGPT these quiz questions. Okay? And 3.5 answered all quiz questions correctly except one. The exception was one in which they had to go and know the difference between instance level locking and class level locking. Okay? And when it didn't, it assumed that they were the same, that the instance method also locks the static methods. So I went and told it, hey, did you realize that the method that's locked here is an instance method? It said, oh yeah, thank you for telling me that, and it corrected its answer. GPT 4.0 got all questions right. So it seems that with more data, we're going to get better results. So then I had some exam questions in my course also. So I said, let's try to see how these guys do with my exam questions. So 3.5 answered all quiz questions correctly except 2. And you can look at the glass half full or half empty, right? I'm looking at the glass half full. So the correct ones had to go and trace unsynchronized code and explain what output you would get. And it did that perfectly. Okay? Tracing synchronized code is not so hard. But the halting problem tells you can't even tell whether the program halts. And here's a program that's telling me exactly what the output should be. Of course, it's saying I may be wrong because this is machine learning, but that's pretty good. And again, 3.5 got the instance level locking wrong. And again, when I told it, that you got it wrong, and it got it right. The second one had to do with detecting a deadlock. Okay? And I hadn't taught deadlocks in my class, but I just thought I'll try it out, see what students do. And I told it, hey, did you realize that you could have a deadlock there? It said, yeah, I got it. And then it gave me the wrong sequence of events that led to the deadlock. 4.0 got all questions right except one. It did not get the deadlock question right. But when I told it, did you consider the possibility of deadlock? It gave me the exact sequence of events. And trust me, those are not easy to produce. And only one student in my class got it right, by the way. Okay, so what are the implications of that I'm trying to imply? So you can look at this stuff and say, oh no, or you can say, oh yes. So, if these tasks that people couldn't do on their own can be done by ChatGPT, well, maybe they'll ask ChatGPT to do it. Okay? If they don't follow the honor code. Okay? And if they're kind of silly because they'll get in trouble in exams. But maybe the counter here is that we give either layered assignments like the one with the Monty Python, which it had a series of 11 assignments to go and build that last scene. Or you give low-stake assignments, which it doesn't matter whether you get it right or not, or you give them in class. Okay? And from my point of view, I give students code, but I never give them model solutions. I'm too lazy to do that. I write exam questions, but I don't give model solutions. So I could use ChatGPT to generate the model solutions and to both quiz, essay questions and code set questions. So my task could become easier. And also, when a student comes to me with a bug, and let's hope they didn't use ChatGPT to fix it, I can use ChatGPT to figure out what the bug is and explain to them what should be done. Okay? So this is sort of the direction. Okay, so I am at my limit, and so let me summarize. We can use programming environment as a visualization of concurrent thread stacks. Okay? We can have custom animating visualizers to show all kinds of interesting things about concurrency. You can visualize the weight queues. You can use an automatic generator to create these simulations. You can have an interactive tool for rubric and navigation management, and you can have both print-based and pure observer-based logging infrastructure. And you can use the logging structure to understand training effort and AI tool. It seems, and I think that's going to be true for other examples too. Converting sequential programs to fork-joined concurrent programs, at least with Java thread abstractions, is going to be no-brainer for these tools. Fixing bugs also may be a no-brainer based on my little experience. Automatic answers to fork-joined questions and load balancing and so forth, I think will also work out based on my examples. And it seems that there's consistency there. One of the problems people have with AI is that sometimes it gives one answer, sometimes it gives another answer, but at least with two examples, it seems to fail, at least 3.5 failed in this exact same, for the exact same concepts. And if cheating the thread, we need layered low-stake in-class assignments. And this is where things get more exciting. If you want to use some of these tools, I'm happy to give you the videos. If you use Java, I can tell you how to use Java also, but that requires some work from me because I don't have any tutorials. There's one can cover other concurrency mechanisms in other languages too. So that's one big goal I have, to build testing infrastructure for MPI, OpenMP, and other concurrency mechanisms. I told you we can visualize, but the visualizations were cheating in my case. We just looked at the logs after the fact. I'd like to build a real-time visualization. I'm not like to be building it right now. And here's another thing. My testing infrastructure could use AI to grade the student work. Yeah, the AI can fail, it's potentially erroneous, but I've got an idea how to fix that problem. And I've shown you how well AI tools did with Java concurrency code. Well, it'd be good to figure out whether they do as well with MPI, with OpenMP code, for instance. Okay? And here's what I really would like to do. So we can tell students don't use ChatGPT directly, and if they're good, they won't do it. But it's good if they don't have to come to you and you use ChatGPT to solve their problems. It'd be good if you can build a tool over ChatGPT that mediates the access, make sure that they don't get information they shouldn't get, and they get information they should get. And that's tricky, but I think that's the future. Sorry if I took extra time, but I'm done now.